Uh, Welcome everybody to this new edition of the High Energy Astrophysics Division seminars. I'm delighted today to introduce our first speaker, who graciously agreed on giving a talk from Japan, where it's currently 1:35 a.m. So thanks a lot. So our first speaker is Takanobu Amano, who is currently associate professor at the University of Tokyo. So he earned his PhD degree in 2008 at the Department of Earth and Planetary Science at the University of Tokyo. He was soon after a postdoctoral researcher at the Solar, Terrestrial and Environmental Laboratory in Nagoya University. He was then, for 3 years, designated assistant professor at Division of Particle and Astrophysical Science at Nagoya University. In 2012, he moved at the University of Tokyo, back to the University of Tokyo, as an assistant professor at the Department of Earth and Planetary Science, GAE. And in 2016, he was upgraded to associate professor. So his research interests includes physics of collisionless shocks, both in the non-relativistic and relativistic regimes, acceleration of transport and transport of high energy particles, theory of kinetic plasma instabilities, both in linear and nonlinear regimes, and numerical technique for kinetic and fluid plasma simulations. Just as a reminder, you can type your questions in the chat and I will read them at the end of the talk, or you can just raise your hand at the end of the talk. So with that, Takanobu, the virtual floor is yours. Thank you.
Thank you very much for kind introduction and invitation with this opportunity. So I'm going to talk about the electron acceleration at the collisionless shock from sub-relativistic ultra-relativistic energies. So I don't think this kind of slide for you guys, but just wanted to remind you that non-thermal particles are everywhere, and almost always, the particle distributions are in parallel. So I'm interested in how this, parallel type non-thermal particles are generated in nature. And of course, the standard theory for acceleration of non-thermal particles is the shock acceleration. And first order Fermi process or diffusive shock acceleration model is a kind of current standard paradigm for accelerating cosmic rays. So particles bouncing back and forth across a discontinuous shock front many times, and they gain energy by repeating this process. And finally, you get the power law. And what this theory predicts is that this kind of a energetic particle profile, this is time profile, but you can just think of it as a spatial profile. So in the upstream, the intensity is low, and as you approach toward this shock, you have exponential increase of the flux, and then constant in the downstream. This is actually observations in the heliosphere. But similar, things are seen also in astrophysical shocks. This is the X-ray observations of young supernova remnant shocks. You see basically the same thing here. So we think this is the mechanism for the acceleration of particles. But there is a problem which we call injection problem, and basically this, you can just think about this equation, which is a particle acceleration time for a given momentum p, and this is proportional to 1 over d mu mu, which is basically a scattering rate in a momentum space, a pitch angle, a scattering rate. And theoretically, the scattering rate is estimated like this, and this is basically delta V squared, and this is normalized to the ambient magnetic field strength, which means that if you have strong turbulence that can scatter the particle efficiently, then d mu mu gets larger, which means that acceleration time becomes shorter. Whereas if you have less turbulence, then acceleration time get longer. And the important thing is that this turbulence power has to be evaluated at some particular wave number. So because particles are most efficiently scattered by turbulence when the wavelengths of the turbulence becomes comparable to the gyro radius of the particle. And if you think about the acceleration of electron, especially at a low energy, then electron gyro radii are very small and much smaller than the typical dissipation scale of the MHD turbulence, which means that essentially there is no power available for scattering electron at a low energy. That's why your d mu mu scattering rate is very small, and the acceleration time becomes very large, and essentially you wouldn't expect the acceleration of electrons by standard diffusive shock acceleration mechanism, simply because there's no scattering. And this is what we call electron injections. We think some typical energy beyond which standard DSA can apply is more or less on the order of 1 MeV in typical industrial medium. And of course, we know observation, synchrotron, of radio and X-ray synchrotron emissions, and we assure that there's parallel tail forming in the relativistic energy ranges. Whereas theoretically, we don't know how to produce particles in between thermal population, some like Maxwellian, up to MeV energy, or maybe GeV. So this is kind of theoretical gap. At the same time, astrophysical observation usually do not provide much of information in this energy range. That's why understanding the electron injection has been so difficult. But luckily, if you look at observation in the heliosphere, so we have plenty of observations by direct in situ measurement of particles and waves. And here's, I'm just showing the example of observation at the Earth-bow shock, which is a shock wave generated by interaction between supersonic solar wind with the geomagnetic fields. And usually electron acceleration seen at bow shock is very weak or even absent. But sometimes we see nice parallel tail, or the spectra is much steeper than you'd expect from a DSA. And if you make a statistics, then you get something like this. So this is a shock alpha Mach number and the TWN, the magnetic obliquity of the shock. And the color show the spectral index. So the reddish color indicate their parallel is very hard, relatively hard, while bluish color indicate the spectrum is soft. And it's clearly harder spectra are preferentially found in quasi-perpendicular regimes. So although we had not been able to understand why this kind of things happen in at Earth-bow shock, because DSA is clearly not applicable naively. But anyway, we know these kind of observations, and if we could understand this process, that may help understand electron injection in more general astrophysical shocks, because the energy range that we are measuring at Earth-bow shock is typically 110 keV or something like that, which is exactly the energy range that you need to understand to resolve the problem of electron injection into basically this energy range. So we're working on this problem, and because the acceleration of electrons is efficient at quasi-perpendicular shocks, classically we think the reason for that is due to shock drift acceleration. So shock drift acceleration is essentially a mirror reflection process. So there is a frame called Hoffman-Taylor frame, which is the frame where there is no electric field, and therefore the particle energy in that frame is conserved quantities. So if you draw a particle, trajectory in the velocity space, this will be parallel and be perp in the Hoffman-Taylor frame. Of course, the particle energy must be conserved, so it must follow on the circle. And particle is essentially coming in toward the shock. So there's some, bulk velocity, and there's some spread around that. And if the particles have sufficiently high energy or larger pitch angle that is determined by the magnetic compression ratio at the shock, then such a particle may be reflected back into upstream, a kind of specular reflection. Although this energy is conserved in the Hoffman-Taylor frame, but if you measure the same process in, for example, in the upstream rest frame, then the particle initial energy is basically the distance between here and there is increased as a result of reflection. And this is a simple mirror reflection process. Therefore, it's easy to estimate what kind of energy gain you would expect. So this is the momentum gain is twice the shock momentum divided by cosine theta Bn. That clearly indicate, further perpendicular shock where theta Bn close to 90 degrees is extremely efficient for this mechanism. But the problem is, this is basically adiabatic process or deterministic process, and therefore it's not able to, produce power law type of, spectrum, which we often observe in, space. So we introduced the scattering on top of this, SVA, and this is called stochastic SVA. So this is a trajectory in the absence of wave, but if you add waves and the waves scatter particles in pitch angle, which is scattering happens in the plasma rest frame. I mean, the energy, is conserved, defined in the plasma rest frame. So if you, for example, start particle from this point, then particle may be accelerating this way, but in between this mirror reflection, particle may scatter in that way along the diffusion curve or constant energy curve. And then particle may accelerate in this way again, but may encounter wave again and scatter in this way. So this is only for lucky particles. But basically, if you repeat this process in a stochastic manner, this process predicts the formation of power tail. And so we have been doing peak simulations, self-consistent, particle simulation for collisionless plasmas. And we sometimes see, so this is a schematic trajectory in velocity space, and similar trajectory is seen in accelerated particle in the simulations. And so we think, the particle trajectory we see in the simulations and what we expect from theory is more or less consistent. And we also look at observations to, check if our theoretical model is correct or not. So it's just a particular shock crossing event observed by NASA's MMS spacecraft. And as I said, usually the electron acceleration across the bow shock is very weak, but this is kind of exceptional event where, we see quite a lot of non-thermal particle populations. So this is electron energy. So this is the upstream region where density is lower. This is downstream region, it's compressed. And in between here is the shock transition layer. So in this particular case, something like 10 seconds or so, this is a shock transition layer. And this is the electron energy spectrum. So in the shock transition layer, you see quite a lot of non-thermal particles with energy like 1 kb, 10 kb, or in this particular case up to 100 kb. So it's kind of exceptional events. Anyway, we look at the data more detail. So there's in the bottom panel, I'm showing the magnetic power spectrum. So we're measuring waves, and this is a wave spectrum. So clearly in this region where you see energetic particles, that power spectrum a lot enhanced compared to the other regions. And if you have these waves, that can play a role for scattering the particles. So I look at the anisotropy, pitch and anisotropy of the particle distribution functions for several different energy channels. And in this panel, so 0 means the particle distribution is completely isotropic. And the negative means particle escaping away from the shock toward upstream. So in the little bit upstream side, the particle is still escaping, toward upstream. But when the spacecraft entered into the acceleration region, clearly the isotropization is happening and the particle distribution functions are more or less isotropic. Because of this, efficient scattering, particle transport, spatial transport becomes diffusive. And if you have diffusion that is balanced by a convection with the upstream flow, then you'd expect the exponential flux increase like this, again, for several different energy channels, but basically we see always exponential flux increase. This is exactly what is expected in standard DSA, but in that case, this spatial scale is much longer than that we are seeing right here. So this is still transition layer. Okay, so but nevertheless, we see particle flux enhancement in exponential profile. So basically, those observations are consistent what we have in mind, but it's rather qualitative. So we are looking at more quantitative evidence of the theoretical model. So what we found is, so basically the theory predicts power law, and the power law must be cut off at high energy. And of course, if you measure the particle distribution function, you can easily determine the cutoff. And theory predicts that the cutoff energy is determined by these equations, and these are basically known quantities. And that means there's only one unknown quantity, which is scattering rate. So if you determine the scattering rate from observations and compare with the observed cutoff, then we can basically check if the theory is correct or not. So this is exactly what we have done. So this is electron energy spectrum. You have power law and there's cutoff. So by fitting power law plus cutoff function, we determine the cutoff energy, which is in this case 20 keV or so. And on the bottom panel, I'm showing the pitch and scattering rate measured from observation in this blue curve. And what the theory tells is that there is some threshold for the scattering rate. And if the measured scattering rate is greater than the threshold, then you'd expect the power law. And if it becomes equal or below the threshold, then you'd expect the formation of the cutoff. And this is exactly what we see in observation. So this is kind of direct proof of a theory with observations. So our idea is that DSA is able to accelerate particle if particle gyro radius are large enough. But low energy electron cannot be accelerated with this process. But if you look at shock transition layer, it's a thin layer and scale size of ion gyro radius. But nevertheless, you have quite intense wave activity there, and we can use that. And if you use such an intense wave activity within the shock transition layer, you can accelerate the particle of sub-relativistic energies. And if this acceleration, continue to some threshold energy for the electron injection, such that particle start to interact with MHD wave out from the shock transition layer, then that's basically the solution for electron injection problem. And we are trying to understand the relations or connection between low energy particle acceleration by stochastic shock drift acceleration and higher energy particle acceleration by standard DSA. So I'm going to skip details, but basically this is spectrums that we expect from theory. So I'm showing the spectrum multiplied by p to the power 4. And in this form, the DSS spectrum becomes flat. So at the higher energy, we expect flat DSS spectrum, and at lower energy, the theory. So this is a kind of theoretical estimate for spectral index. Basically, the spectrum becomes steeper than you would expect from DSA. So this is kind of theoretically expected spectrum. At lower energy, you have a steeper spectrum all the way up to some depending on the parameters, but it's like 0.1 MeV or 1 MeV, something like that. And beyond that, if the conditions some certain conditions are satisfied, then you expect the formation of high energy tail in a relativistic energy range. So I guess I'm running out of time, so just want to skip this. But basically, we are trying to understand the acceleration of electron from low energy to all the way up to high energy, and we have kind of model and can explain very well the available observations. And one of the applications that we have in mind is, astrophysical. Of course, in a young supernova remnant shock, you have plenty of observations. But if you look at the X-ray range, typically X-rays are emitted from synchrotron emission from TeV electrons. But sometimes you see a non-thermal bremsstrahlung emissions, and that emission is directly coming from sub-relativistic electrons. So we may potentially prove our theory also with the astrophysical observations of supernova remnant shocks. And yeah, that's it. If you have questions, you can take it.
Thank you very much for this fascinating presentation. Do we have questions? I see John raised his hand. So John, please.
Hi, that was very interesting. I have a question. You mentioned one kind of threshold. I was wondering whether there is a threshold shock speed or Mach number or something like that.
Yes, actually, I don't have threshold here, but yeah, there is threshold, and it's difficult to give, how do I say, exact conditions, but basically we expect, I probably don't have that. Alpha Mach number divided by cosine theta Vn is what we think is an important parameter. And if it's large, then basically we expect, this kind of process becomes efficient. So both alpha Mach number and, theta Vn.
Right.
Sure.
Okay. There is some evidence. There's a recent paper by Tutone et al. About the Cygnus loop, and it seems as though there is efficient acceleration in the shocks above maybe 300 or 400 kilometers per second, but not in the slower shocks. They seem to just use the ambient cosmic ray population of electrons and ions. Thank you.
Thank you.
Thanks. Do we have further questions? Can see, maybe I can ask one myself. We still have some time. So you were talking about Whistler waves with high frequency in the shock transition layer as a scattering agent. So what is the origin of these waves? In your model, you assume they are pre-existing, or they might be excited by the electrons themselves?
Yeah, it's a very important question. And currently, we are just assuming the presence of waves. I mean, we have observations, so we know the waves. And if the wave is strong enough, then we can explain this kind of things. But of course, these waves must be generated by some instabilities or something like that. And what we currently have in mind is that these waves themselves are generated by accelerated electrons. So there's probably some self-regulation process going on, electron acceleration going on, and then that generates waves, and then acceleration becomes, how do I say, sustained. That's what we expect, but we haven't yet, show that.
So are you thinking about some sort of two-stream instability within the shock layer?
Depending on wave frequency, higher frequency waves probably generated by sort of temperature anisotropy driven with thermal wave, and at lower frequency, there are several different candidates. One of them candidate is electron sort of heat flux like kind of beam. Yeah, that's right.
Okay, thank you. Don't see raised hands, so I'll move on to the second speaker. If you have a question, you can probably still ask Takanobu. I don't know if you are remaining online because now it's 2 a.m. for you, so at some point you might want to leave. But if people want, can still probably post the question on the chat. So let me move to our second speaker. Thanks a lot, Taka. So the second speaker is our own Peter Maksym. So he earned his bachelor degree at Yale, worked for 5 years as a Chandra data specialist, and then earned his PhD at the Northwestern in 2012. He's been postdoc at the University of Alabama and at CFA, and is currently an astrophysicist at the CFA, working on multiple projects related to the supermassive black holes and their accretion and growth, and their interaction with host galaxies. And with that, Peter, the floor is yours. Thank you.
All right. Thank you, everybody, for attending, and thank you for the introduction. Am I muted? No?
No, we can hear you.
Okay, good. Yes, I'm normally hosting these things, but when there's a last-minute change of plans, it's helpful to have someone who can give a talk. This is somewhat condensed from a longer talk under a relatively short time, so hopefully I'll be able to fit everything. But one of the galaxies that I've been working on recently with our group is IC 5063. So several of the people in the audience are collaborators. IC 5063 is an interesting target of study because it's only at 50 megaparsecs. It is one of the most radio loud Seyfert-2 galaxies in the local universe. It's been long known to have an evolved merger, and because it's relatively close by, and the nucleus is obscured, it makes it a great target for studying strong AGN feedback. It's been the subject of high-resolution studies for a couple of decades now. Both of these images are from a 1998 paper by Morganti et al. Using Hubble data. And if you see the inset on the left, the image on the left is continuum band, optical continuum from Hubble with starlight, and the inset is radio contours. You see a compact jet that is directly in the plane of the galaxy, interacting with dense clouds at a few hundred parsecs from the nucleus. But the contours from the larger image are O3. You have these spectacular X-shaped O3 features that extend well beyond the galaxy. And if you look at the contours on the right, the image is O3. The contours are from neutral hydrogen, 21 centimeters. And that emphasizes that the jet is in the plane of the galaxy, and the bicone from the AGN is obscured at small angles due to the plane of the galaxy. It's just at the large angles that you see tracers of O3 emission in the Hubble data out to thousands of parsecs. So the model that we have for this particular galaxy is very unlike, say, our Milky Way, where you can see the Fermi bubbles in Rosita on the lower right-hand image. You have a jet that's inclined directly into the plane of the galaxy. It's impacting these dense molecular clouds that are also relatively close to the nucleus, but we can still resolve it, which makes it a great laboratory for studying AGN feedback. More recently, it's been studied with ALMA, and in this figure from Oosterloo et al. In 2017, the contours are the radio continuum, so you can see the two lobes from the jets that are interacting with nuclear molecular gas. But the color image is carbon monoxide line ratios, which are a rough indicator of temperature. And so where the jets are impacting the molecular gas, you have these elevated carbon monoxide ratios, which is about 100 Kelvin at the max. But there's also evidence from this ALMA study that there's an expanding cocoon of hot gas associated with these outflows. These molecular clouds are pretty dense. They'd be Compton thick after about a parsec if you had that much in a single column. And so our group has been involved in a deep Chandra study of IC 5063. And we know that to first order O3 and soft X-rays are spatially associated in AGN bicones, and it's been thought previously that this is a single photoionized medium, that the X-rays are probably photoexcited, but the spatial association is more complex when you look at it in high resolution with good quality data. You can start to tease out where the collisionally excited gas is and where it's photoexcited, and that's exactly what we want to do with these large with this 250 kilosecond study that Pepe is PI for. One thing that we had to go along with it is Hubble data. And the reason for that is because in principle, you can look at each parcel of gas in the galaxy and categorize it as to whether the ionization required is consistent with Seifert-2, with an AGN, so it's Seifert-like, or whether you could do it by photoionization, or it's more like a liner. And so these data are from MUSE, where you can get a spectrum at each point. And again, you can see that large X-shaped feature is consistent with, in red, Seifert-like emission. You've got streams of gas that are consistent with star formation outside of the bicone, and then perpendicular to the bicone, you have these green blobs, which are liner-like. Now, this is MUSE, so you're limited by the Strel ratio and by seeing, and so these data are only about 0.8 arcsecond resolution, but with Hubble, you can get down to 0.04. Your spectral resolution is not as good, but you can reasonably model the aggregate situation within the narrow filter if you make some assumptions about the contributions of, say, nitrogen-2, which contaminates H-alpha. So while I was working on the Hubble data, this was in happier times when we could all gather in places like 20 years of Chandra. And you can see Pepe and Martin sitting there on the left, and I, being involved on Twitter, I'm trying to share the things that I see, but also paying attention to what other people are doing in the world of science. And if you don't know Judy Schmidt is not an astronomer by training. What she is a very experienced amateur image processor. She's extremely good at this. She does it all the time. Anytime a Hubble image of something extended, like a planetary nebula or a galaxy, becomes public on the archive, she takes a look at it and creates these beautiful images that you see below. And on Wikipedia, a huge fraction of the beautiful images that you see on Wikipedia were actually processed by her. So there's a parallel, there's another program going on for IC5063 at about this time, PI by Aaron Barth. And it because it's a SNAP program, it became public immediately. It was a survey of AGN that had been detected by Swift's burst alert telescope, so good evidence for hard X-rays. These are F814W, so 8,000 angstrom continuum images to study the properties of the host galaxies that are known to have hard X-ray emission associated with the AGN. And Judy, with her many years of experience looking at lots and lots of different things, is able to tease out some unusual features. You see these lines to the southwest of the nucleus radiating. You have to squint really and get a good stretch, but she did that, and she marked it out on her Twitter post. In this continuum image, there are these radial features, which is surprising. We know what the host galaxy is doing in narrow lines. You look at an AGN that has a bicone, and it's excited in O3 and H alpha and all these nebular lines, and that's all in the plane of the galaxy for IC5063. So what could you do to produce these continuum features? Of course, a lot of professional astronomers are really love Judy's posts on Twitter. And so a whole bunch of people start chiming in, and you get this really exciting discussion of these novel features in real time. You can see the discussion online. How did this play out? And how do we decide what's going on for something that a large number of people are excited to see? Bill Keel was the first person to model the distribution of the continuum emission according to ellipsoidal profiles, and that really brings out the positive and negative residuals that you might get from what Judy did with the stretch. And you see these bright radial, you see the dust lanes that go across the galaxy along the plane of the galaxy. And then you have these bright radial features and these dark radial features that are along the same direction that Judy drew her lines. What's going on here? Bill had the idea that maybe what we're actually seeing is what has been speculated to occur with AGN for some time, but to our best of our knowledge has never been seen, what he called crepuscular rays. Now, crepuscular rays on Earth's atmosphere are when you have the sunset, the sun's just below the horizon, you have scattering by water and dust in the atmosphere, and you only see dark and light patterns based upon whether the sun is obscured by clouds near the horizon or not. You can think analogously that there might be clouds near the AGN, and so you've got scattering by something in the galaxy that causes you to see it. In this case, you can have scattering by a dusty halo. And that's the subject of the press release that we had a year ago. This image has, for blue, sulfur 2, that is from our HST program, and also in green and red, the continuum bands from both our program and from Aaron Barth's SNAP survey. But, and we know that this is not, we can say with confidence that the residuals from the ellipsoids are very significant. The azimuthal profile for, it's about a 1 arcsecond wedge across these dark cones is good to 20 sigma at certain points. And they're also significantly dark relative to the brighter features out to 30 arcseconds, which is well over, it's like 10, 15 kiloparsecs. So this is interesting, but how do we explain it? And so we played around with a number of ideas, none of which we're entirely certain with. One of them was the major focus of the press release. Our 0th order is that these are continuum features, so they've got to be starlight. But we also explore the idea of whether they might be corpuscular rays, in this case, the shadow from clouds near the nucleus, or something associated with the outflows, which we know exist, they just happen not to point in that direction. So one possibility is that we know that the AGN is pointed in the plane of the galaxy, and we know that this is a Seyfert-2 galaxy, so it's obscured in our direction, which geometrically implies that you could have a torus or toroidal-like structure around the galaxy that is obscuring the AGN in the directions of these dark rays. Obviously, they're not uniform. They've got these bright streaks in the middle, which could be produced by gaps that allow light from the AGN to penetrate, and then it all gets scattered off by a dusty halo that's distributed throughout the galaxy. One possibility that would be might naturally produce that bright gap in the middle is if you have an extended disk that's large enough where the self-gravity becomes unstable and the disk is warped, and then you can have clouds that are settling at different preferred orbital angles, and the gaps in the disk allow light to pass through. Our null hypothesis is starlight, and certainly we know that this is an evolved merger. So one thing that you can get is extended shell-like features from stars settling into their settling into these shell-like patterns. And if it's evolved enough, then they start to diffuse out of their shells, and so it starts to look like an hourglass, as you see in the model on the upper right-hand corner. The main problem with that particular interpretation for IC 5063 is that the angles for the edge of these stellar fans are relatively steep, and people who simulate these things don't seem to see angles that steep. They're narrower, like you see in the figure on the upper right. So we don't think that's very likely. One thing that is I think more likely than we had considered before is the fact that you have the jets that have been they're impacting the molecular clouds, and of course the hotspots that you see, the bright O3 emission and the radio blobs, are just the areas of most intense interaction. But IC 5063 has been simulated and by Mukherjee et al. In order to describe the effects of feedback on the galaxy. And it's entirely plausible that you have hot plumes of low density gas, 10 to the 8, 10 to the 9 Kelvin, that are expanding from the nucleus in lateral outflows, and that these can lift dust and gas into the cross cone of the AGN. And so if you lift enough dust into the cross cone, then that can obscure the AGN continuum. Light doesn't reach the dust in the extended halo, and you don't see anything. You have a dark feature because the light's just not making it that far. An alternative possibility is that these hot outflows, these hot lateral outflows, are continuing to expand to tens of kiloparsecs. And along the way, they don't just lift dust and gas into the cross cone, but they entirely displace it. We know that if it's 10 to the 8, 10 to the 9 gas has been speculated, then that's more than hot enough to destroy dust, which is destroyed at a couple thousand Kelvin. And we also know from, I didn't explain this Hubble image on the lower right, that's from our program. when you look at the nucleus, the inner 10 arc seconds, the structure in sulfur-2 is filamentary. You see loops and bubbles that are consistent with gas that is escaping laterally along the path of least resistance and lifting moderately dense material as it goes, possibly producing shocks. So we have additional data in X-rays that also seems to point to this scenario of a vacated or dusty cone, a cone that's produced by an outflow where it either obscures the AGN or it completely vacates the dust so you don't have any reflection. The 250 kilosecond program in Chandra shows that the X-rays near the nucleus are extended to a couple of arc seconds at a wide variety of energies, but most relevant to the idea of a vacated or dusty cone is that when you do imaging spectroscopy within the bicone, you have strong evidence for photoionization, but the X-rays are also extended in the cross cone, and that's collisional gas. So we have evidence for hot gas that is escaping laterally near the nucleus. So that's the picture that we get when we look at the HST data, where we have imaged sulfur-2, H alpha with the nitrogen subtracted, H beta, and this gas perpendicular to the bicone is clumpy, it's filamentary, and when we take the BPT maps, looking at whether the emission is what kind of emission do we have in the bicone? It's Seifert-like, but as you move away from the bicone, it rapidly becomes liner-like, like you see at the Muse data in the Muse data. But this transition happens on parsec scales, even tens of parsec scales, and the bubble that we see perpendicular to the nucleus in the Hubble imaging that's very strong in sulfur-2 is liner-like, and we think is probably associated with precursorless shocks, since it's expanding into hot X-ray gas that's largely photoionized. You don't have the precursors that might otherwise generate O3 emission for fast shocks. And there's also evidence for these outflows, these lateral outflows perpendicular to the bicone from follow-up Muse studies by Venturi et al. When you just look at the high velocity gas, even if it's very faint, you have this chimney of high velocity O3 that is detectable out to tens of kiloparsecs. And so that's also consistent with the idea that there's a lateral outflow that may be, for example, clearing the dust and making it impossible to reflect continuum emission that the observer would then see. So that is the end of the story, although the idea that this is the shadow of the torus is very interesting, and I've had people comment that the residuals in the continuum image are very sharp, and therefore it doesn't sound like it's plausible that it's some kind of outflow related structure. I think that the bulk of the evidence points to some sort of galaxy scale lateral outflow. And I think that's it for now.
Thank you so much for Peter for this nice presentation. And this teaches me also that I need to use Twitter much more. So do we have any questions in chat? I don't see anything. Let's see. Raise hands. Don't see at the moment. Raise hands. Okay, while people think about this, I just want to thank again Peter for stepping in because we had a last-minute cancellation, so it was very nice from him to shorten and trim this previous presentation. Another thing, we have especially for appointments available for Takanobu, so there are still slots available. So if you want to sign up, if the time doesn't match yours, you can easily email him and set another time. As for Peter, is internal, so you can email him anytime you want, as our email was specified. Don't see questions here. All right, okay. Let's assume people need to think a little bit longer. All right, okay. So with this, thanks to everyone, and we'll see you next week. Thank you.
Thanks, everybody.